For this example, we are going to look back at the same example we saw in the prior section. However, instead of doing it in the way that we did in the prior section, we're going to use the observed significance of the test, or the p-value approach. So let's look at this same problem that we did in example 5. A cosmetics company fills its best-selling 8-ounce jars of facial cream by an automatic dispensing machine. The machine is set to dispense a mean of 8.1 ounces per jar. Uncontrollable factors in the process can shift the mean away from 8.1 and cause either underfill or overfill, both of which are undesirable. In such a case, the dispensing machine is stopped and recalibrated. Regardless of the mean amount dispensed, the standard deviation of the amount dispensed always has a value of 0.22 ounces. A quality control engineer routinely selects 30 jars from the assembly line to check the amounts filled. On one occasion, the sample mean is 8.2 ounces and the sample standard deviation is 0.25 ounces. We want to determine if there is sufficient evidence in the sample to indicate at the 1% level of significance that the machine should be recalibrated. Now, let's recall what we did when we did the example before. We went ahead and we stated our null, which is exactly the same. The mean is equal to 8.1, and the alternate was that the mean was not equal to 8.1 because we cared whether it underfilled and we cared whether it overfilled any jars. So we needed the not equal to. And then alpha was 0.01. Now you might recall in the last example, what we had to do next was to find our critical values by taking our 0.01, dividing it by finding out what those z values were for both of our rejection regions. Well, with the observed significance method, we're not going to do that. We're going to go straight to finding our test statistic. So we do our test statistic in exactly the same fashion that we did in the example before. So this is exactly the same calculation we saw in the last example and exactly the same answer for our test statistic. And let's remember that this formula was our test statistic. All right, now once we've got our test statistic in this particular method, we're going to use Excel at this point to look up the p-value for 2.191. All right, so let me go ahead and open Excel and we're going to put that in. All right, so in Excel, we're going to type in equal norm.s.dist, and we're going to put in 2.191 and the word true, and we get 0.985774. Now this is not our p-value. Let's remember that when we were looking at a picture of this, we had two tails. All right, and this right here is the probability that we have a z-value less than 2.191. And what we really want to look at, since we're looking at a tail that's really to the right, we want to subtract this from 1. And I'm going to take it out 4 decimal places because most of your exercises are for 4 decimal places. Now this gives us the value to the right of our 2.191, or the area to the right of our 2.191. Let's remember that this is a two-tailed test, so we also want to consider the area to the left of negative 2.191. Easiest way to do that, though, is just to double the area that we just got. And that's going to give us 0.0284. So this is our p-value. All right, so our p-value is equal to 0.0284. All right, now if the p-value is less than alpha, we reject the null. And if the p-value is greater than alpha, we fail to reject the null. So let's notice in this case, this p-value is greater than alpha, so we fail to reject the null. This is exactly the same result we got when we did it in example 5. It's just that we found whether to reject or not to reject based on this p-value and alpha rather than based on our critical values. All right, so we failed to reject the null. Let's now make our final statement. There is not significant evidence to reject the null. And we can state that p-value is equal to 0.0284. Notice we state the p-value this time instead of alpha. It appears that the machine is still calibrated correctly. In other words, it's not underfilling or overfilling. We are still looking at this situation right here. Now, before I finish this example, I want to state a few things about p-values that will help you. So when doing p-value examples, if your alternate is less than, then look up your test statistic in Excel and report the p-value. All right, so in other words, you're going to look up, if this had been a less than, then you would have just looked this up, and the answer that we would have gotten would have been the p-value. Okay? If the alternate is greater than, you're going to look up the test statistic in Excel and report the p-value as 1 minus whatever the probability you obtain is. All right, so in this instance, you notice the first thing that we did, because this was on the right, we had a two-tailed test, but if this had been a greater than, because this was on the right, we would have subtracted it from 1, and that would have been our p-value. And I should say what the p-value is 1 minus the probability you get. All right, and then the alternate is not equal to. Well, there's really two scenarios here. If your test statistic is positive, like it was in this one that we just looked at, this test statistic was positive. We look up first. We look up in Excel, and then we subtracted from 1, and then we doubled it. All right. However, if the alternate is not equal to, if the test statistic is negative, we look it up in Excel, but we don't have to subtract from 1 when it's negative because it's on the left tail. All we have to do is double it to make up for the right tail, since we've got 2 tails. All right, so hopefully that's going to help you through some of these p-value type problems.